Hello everyone, and welcome to the session on IP MPLS fundamentals and positioning. This session should give you a high-level overview of the IP MPLS technology, including protocols for label distribution, as well as Layer 2 and Layer 3 services running over IP MPLS network. Becoming more familiar with IP MPLS should help you better understand its capabilities and therefore better position it with or versus some other technologies on the market today. Let's get started. So let's start with IP MPLS basics. Let's first agree about MPLS terminology and naming convention, so we will be all on the same page when talking about different node positions and functionalities in the network later on. From positioning point of view, you have nodes that are completely outside of MPLS domain, and they are called CE or Customer Edge Routers. You have nodes that are placed at the edge of MPLS domain, so those nodes are called PE nodes or Provider Edge Routers, and there are nodes that are completely within MPLS domain. Those nodes are called P nodes or Provider Core Routers. So now from MPLS functionality point of view, imagine that you have a flow of packet stream from left side CE towards right side CE. So the first PE node on its path will be Ingress Label Edge Router or ILER. Its task is to receive non-labeled packet, push a label on it, and forward it further through MPLS domain. LSR or Label Switching Router functionality is to swap labels of the packet on its path. So it will remove ingress label, it will add egress label, and send the packet further on. At the egress edge of MPLS domain, you have Egress Label Edge Router. Its task is to pop or remove the label and send the packet further as a non-labeled packet towards the right side CE. So those functionalities that I just mentioned as ingress or egress LER will be opposite on the flows from right side CE towards left side CE. So this PE for those flows will be ingress LER and this PE will be egress LER. More details about this naming convention as well as some other basic about MPLS you will find in RFC 3031, so it's a very good point to start with. So let's see what is control and data plane of MPLS made of. Every MPLS node, regardless its position as a P or PE node, needs to run IGP protocol on their interfaces such as ISIS or OSPF to peer or make adjacencies with their neighbors, exchange routing updates, and build their routing information base. This is a standard process of routing network as we know it. For the same destination within routing information base, there could be multiple alternatives, and using metrics, the best path is calculated and the best route is chosen and placed in the route table. The copy of route table is then placed in network cards and network modules of nodes and used for data plane as forwarding information base. This forwarding information base is used for all IP forwarding. At the same time and parallel to IGP protocol enabled on interfaces, one has to enable also protocol for label bindings exchange, such as LDP or RSVP. Both protocols will be described in more details later on. Those sessions between neighbor routers are established and label bindings are exchanged for IP prefixes known in the network. Similar to IGP tables, router will create a label information base with information what labels are used to reach certain IP prefixes in the network. There might also be redundant label entries to reach certain prefixes in the network, therefore the best label entry by which label packet will be forwarded along the LSP path will be copied to network interface cards as label forwarding information base and will be used for MPLS data plane. All above-mentioned tables reside on MPLS nodes and are accessible to network administrators. Here you can see how the MPLS nodes in the network use those tables. Let's first define two new logical entities here. The first one is forwarding equivalent class, which is similar to IP prefix in IP world. Here, in addition to IP prefix, additional criteria or constraints could be added by administrator. The second one is LSP, or label switched path, which is basically logical path between LERs. LSP is also called transport tunnel, and it is important to say it is unidirectional. So in case you want to have a two-way communication, two LSPs have to be created. As you can see, communication on IGP level and label level is ongoing through established sessions between routers. So in this example, an IP packet, although different formats are supported, ingresses a router. Looking at the forwarding information base table, router learns that IP prefix or forwarding equivalent class is on another LER. Therefore, it is reachable through MPLS network. For that reason, there will be a lookup at label forwarding information base table in which there is already defined label for that IP prefix, and the label will be pushed to the data packet between MAC and IP header. As such, the labeled packet will be forwarded to the next hop router. Next hop router will check incoming label, will take a look at its own label forwarding information base for outgoing label, and will perform label swap, meaning removing or stripping off incoming label and placing outgoing label, and will forward packet further through egress interface to the next hop MPLS router. This process will continue until data packet reaches egress LER. In label forwarding information table of egress LER, there will be no more egress label for that IP prefix. Therefore, the label will be popped and data packet will continue its path without label. Next step is a lookup at forwarding information base in order to see through which interface data packet will be forwarded. In case any of MPLS routers receive a label packet for which it doesn't have an entry in its label forwarding information base, this packet will be discarded. So basic operations with labels are push at ingress LER, swap at LSRs, and pop at egress LER. Just a note here that segment routing is doing this a little bit different. At the ingress LER, multiple labels will be added, one for each router on the path, and when the packet arrives to the LSR, it will pop the top label and will take a look at the label below in the stack, now the new top label. It will take a lookup at its label forwarding information base table and will find entry for that next hop router where the packet will then be forwarded. On every slide so far, we talked about MPLS labels, so let's take a look in details what this label really is. First of all, you can see it is placed between layer 2 header and layer 3 header. That's the reason why MPLS is set to operate at 2.5 layer. Label itself is 32-bit long and bits are divided as follows. Label value is 20-bit long. This is the part based on which you are doing MPLS switching. The router looks at the ingress label and swap it for egress label based on forwarding label information base. That egress label is of course ingress label for the next hop router along the path, as already is established. The label range goes above million, but keep in mind that some ranges are either reserved or internally used. However, the vast majority is available for MPLS switching of data packets. Next field is experimental field that occupies 3 bits. It's called experimental because when initially labels were introduced, it was not clear for what purpose this field will be used. But nowadays it is used for quality of service, so something completely opposite of experimental meaning. You can also see names such as traffic class field in some documents instead of EXP field. S-bit is a single bit that indicates bottom of the stack. Not sure if I mentioned earlier, but multiple labels can be stuck upon each other in a label stack for different reasons. One reason is service label that defines service ID opposite to transportation label that defines transport tunnel. Another example of MPLS stack would be for fast reroute. Transport label is always outer label, the first one behind layer 2 header. In this example, you will see that label 1 has S-bit set to 0 as it is not the bottom label. Label 2 is inner label and has S-bit set to 1. The last field is TTL or time to leave field and has the same functionality as TTL field in IP packets to prevent from infinitive forwarding. Its value is decreased by 1 by each LER or LSR, and once it reaches 0, this packet will be discarded. Just like in every other networks, we also need quality of service in MPLS network in case of network congestion. When that happens, it is mandatory to prioritize packets, meaning to assign different priorities to different packets, allowing some of them to be forwarded, some delayed, and some discarded. The whole quality of service concept is very complex and includes, to name just a few steps, classification, queuing, scheduling, marking and remarking of packets. And it is all controlled using quality of service policies that would be applied to different parts of packet path through the MPLS node. As you already know, at layer 2, for marking purposes, we can use 802.1 p bits as a part of 802.1 q tag within a layer 2 header. At layer 3, we can use type of service bits for IP precedence or differentiated service code point or DSCP as we know it. As mentioned previously, there is 3-bit field within MPLS label that is used for marking purpose. Using this 3-bit, label packets are assigned to one of 8 different forwarding classes as listed here. There are basically 2 modes for handling traffic class bits in the MPLS network. One is called uniform mode, and in that mode, usually the 3 most significant bits of the DSCP field are copied into traffic class bits at ingress LER. On its path to egress LER, this traffic class field value could remain the same or could be changed due to different quality of service requirements and policies along the path. On the egress LER, the value of traffic class field will be copied to DSCP field in the IP header, regardless if this value was changed or not through its path through MPLS network. In our example, you will see that unlabeled packet with DSCP value of 5 is arriving to router 1. Router 1 will copy this value into experimental or traffic class field. Along the path, this value of 5 will be changed to value of 3 due to quality of service policies. And you will see that on egress LER, when packet is leaving the MPLS domain, that traffic class field or experimental field value will be copied into new DSCP value of IP packet. The other mode is pipe mode, in which experimental bits or traffic class bits are explicitly set at ingress LER, and as such could also be changed according to quality of service requirements in the network. These values within MPLS header will be used for MPLS network only. At egress LER, when all the labels are removed, the packet will continue with its original DSCP value. As you can see in our example here, unlabeled packet comes with DSCP value of 5, and regardless the changes in experimental bits in MPLS header, The packet will leave MPLS domain with original DHCP value of 5. Let's mention here that we are talking about link LDP protocol, which is used to establish transport tunnels. There is also targeted LDP, which is used to establish service tunnels for service demultiplexing. So when packet arrives at destination LER using transport label, service label will be used to assign traffic to appropriate service. First step is to enable link LDP protocol on all the interfaces of adjacent routers and establish LDP sessions among them. When this is done, based on LDP mode of operation, which is downstream unsolicited mode, every router will start to advertise local IP prefixes, including system interfaces. Unsolicited mode means that routers will do this by default, without being prompted for such an action. So in this example, router R7 will advertise its system interface 1.1.1.7 to adjacent routers, and will also advertise expected ingress label for that IP prefix, which is 123.123. In its LIB, label information base, it will have all 3 entries because this information was sent to 3 different routers. While in label forwarding information base, there will be only a single entry that can be read as label 123.123 is the expected label for IP prefix 1.1.1.7. Prefix 1.1.1.7 is a local, therefore label operation is POP, meaning router 7 will remove label 123.123, no new label will be added, and packet will be sent further according to forwarding information base. Here you can see example for router 7, but all routers are doing just the same for their system addresses and all IP prefixes for which they could be reached. In this example, once routers 5, 3, and 6 receive this information from R7, they will enter this information into their label information base and will flood this information about prefix 1.1.1.7 further to their adjacent routers, except the one from which this message was received, which is R7. As a result, a full mesh of transport tunnels will be automatically created in order to reach each of system IP addresses. Let's see what will be in the label information base table of router 5 after flooding of all LDP messages. In the label information base table of router 5, there will be 3 entries for prefix 1.1.1.7, as R5 will receive reachability for 1.1.1.7 from 3 adjacent routers, router 2, router 3, and router 7, informing router 5 what ingress label is expected in order to forward data towards IP prefix 1.1.1.7. They also expect router 5 to set those labels values as its egress, as they have to match. As we already know, one router egress label has to match next hop ingress label within LSP. With those 3 entries in the label information base, router 5 will take a look at forwarding information base table, which clearly says that prefix 1.1.1.7 is reachable over the next hop interface, which is configured on the direct link between R5 and R7. As a result of computation with those 2 tables, the router will place the best match single entry into label forwarding information base, saying in order to send data to prefix 1.1.1.7, I expect ingress label 131.222. I will then do label swap, so the new label will be 123.123, As you remember, this was set by router 7 as we saw on a previous slide. And router 5 will then send the data on interface 117 towards R7. Previously described process will be done by each router in the MPLS domain, having enabled link LDP protocol on their interfaces. This will establish full mesh of LDP tunnels for all nodes and related IP prefixes. If you take a look at the tunnel table on one of routers, you will see there is an entry for every IP prefix in the network. You can also see what protocol is used to establish this tunnel, next hop interface, and calculated metric to the destination. You can see LDP protocol for each tunnel because it is not mandatory for the whole MPLS domain to run only a single distribution protocol for labels, so you can have tunnels created over LDP or RSVP protocol. Also, as you notice, you will not see all the hops for the tunnel, just the next hop. To see all the transit routers for one tunnel, you can use OAM process such as LSP traceroute. I have to mention here that all the tables shown here are simplified and they don't really reflect the table look or content of any manufacturer. So please keep this in mind once you work with the real MPLS routers. Let's now move to another protocol that is used for label distribution, which is called RSVP, or Resource Reservation Protocol. Even better said, RSVP-TE, where TE stands for Traffic Engineering. What does traffic engineering basically mean? It means deviation from regular shortest path calculated by IGP such as ISIS or OSPF. We still need ISIS and OSPF in MPLS network, but in order to use traffic engineering for label distribution, we also need to use traffic engineering capabilities and extensions of ISIS and OSPF. With these extensions, ISS and OSPF could advertise different constraints network administrator will put on the LSP and would be able to use those constraints into account when calculating the shortest path to destination. Those are enhancements to IGP protocols. Related to creating LSP path, RSVP-TE protocol has also a set of messages exchanged between routers along the LSP path. Path messages are sent from head-end router, the router at which LSP is configured, towards tail-end router, router on which LSP terminates, with the task of checking the availability of resources. RSVP reservation messages are sent in the opposite direction, so from tail-end towards head-end router, and are used to confirm required resources in order to establish LSP. In case resources are not met, an RSVP error message is sent to head-end router from the first router on the path that does not meet requirements. In this example, you see that LSP from router 1 to router 7 will be successfully established, while LSP from router 1 to router 5 won't. Opposite to LDP LSPs, an RSVP LSP is explicitly requested by network administrator. So if there is a need at router 1 as ingress LER to have router 7 as egress LER, a network administrator has to configure such an LSP. So what are real operational benefits of all the traffic engineering capabilities in IGP and label distribution protocol? First of all, with RSVP, you can have a full control of LSP path through the MPLS network, regardless underlying IGP. You can manually set all hops in your primary path, as well as you can create a multiple secondary path with, again, explicitly configured hops. As a best practice, it is always good to leave one path to be created by IGP as a last resort solution. In this example, you will see that there is a primary path explicitly configured with nodes R2, R5, and R7. First secondary path will be R4, R6, R7, and the second secondary path in case primary and first secondary fail, it will be R3 and R7. Besides administratively defined paths, traffic engineering capabilities can be used for dynamically establishing paths using constraints into account. As you can see, there is one example in which you can configure LSP from R1 to R7, saying to avoid previously set red lines. So if those lines are colored by red, dynamically configured new LSP would avoid it. As you can see here, the only solution is to create LSP through hops R2, R3, R5, and R7. It is also possible to configure LSP in a way that secondary path is not allowed to use any link that is used by primary path. Another example could be that you can configure LSP with a constraint that every link needs a minimum of 1 gigabit per second available bandwidth. By this constraint, you will automatically rule out all the 1 gig links in the network. By using RSVP, you can also configure point-to-multipoint LSPs for multicast traffic, such as video broadcasting, and avoid using multicast protocols in the network. Another benefit provided by RSVP-TE is fast reroute. I believe many times so far you have heard about fast reroute and its 50 milliseconds convergence time. Fast reroute basically is capability of MPLS routers to automatically establish protection for primary path in case of failure of link or node along the path. Every router along the path of LSP will create and signal a tunnel through which traffic will be steered to bypass directly connected link or adjacent router along the path in case of failure. This functionality is done only by enabling fast reroute capability within LSP at the head-end router. None of the routers along the path have to be additionally configured for fast reroute functionality. Related to fast reroute, besides head-end and tail-end routers previously described, we should also become familiar with point of local repair, which is a router where protection tunnel originates, and merge point, a router where protection tunnel terminates and merges into original LSP path. In this example, we have LSP with primary path that goes through hops R2, R5, and R7. As previously mentioned, R2 router, as well as other routers along the LSP, will have pre-signaled bypass tunnel in case of link fails between R2 and R5. This bypass tunnel will go through R3 and going back to R5. So in case a real failure occurs, R2 will steer the traffic over the R3 and R5. So this traffic will not be black hole. It will be steered over the bypass tunnel until the error message that was also sent by R2 towards R1 as a head-end router, until this message is received and processed by R1, and then R1 will start to use secondary path that is configured between R1 and R7 through nodes R4 and R6. So 50 milliseconds convergence time is achieved due to this bypass tunnel that is provisioned and signaled before the error occurs. I would like to mention here that 50 milliseconds is not end-to-end convergence in the MPLS network. It is only LSP convergence. So far we have seen how to create an LSP, either fully dynamic, with or without constraints, or manually hop by hop. If you remember the LSP table with LSPs that were created using LDP protocol, this table gives you just the first hop router, with a couple of OAM tools, where OAM stands for Operations, Administration, and Management. We can detect data plane failures in LSP. Those tools are LSP ping and LSP trace, and they are modified after the ping and trace tools in IP networks. With LSP ping, administrator can verify if egress LER is reachable as you are pinging IP prefix that is connected to egress LER. With LSP trace, administrator performs control plane checks of all transit routers for the LSP. With LSP ping, the sender node encapsulates the echo request for the destination prefix in transport label. Every transit node will have to perform label swap until egress LER. If prefix is present at egress LER, this node will send echo reply with system IP address as a source address. Echo reply doesn't use LSP, and there is no encapsulated label to it. As all LSPs are unidirectional, echo reply is using IGP table for return path. LSP trace or traceroute utility also uses echo request and reply messages, same as in IP world. It starts with time to live equals 1. The first scope router checks for the presence of IP prefix in its label database. If it finds a prefix with an egress label mapping for the prefix, it means it is a transit router and sends appropriate code in its echo reply message. Those echo reply packets are also sent unlabeled and are using IP routing tables. In the next iteration, sender node increases time to live to 2, and so on until echo request reaches the egress LER. Echo reply message from egress LER has a different code than those of routers in transit, indicating this is egress LER. This code indicates to sender node that there is no need for a new echo request with increased time to live field anymore. There is also LDP ECMP traceroute feature that allows LSP trace to discover all ECMP paths for a given IP prefix. Let's move now to IP MPLS services. As you know, we do resell Nokia MPLS products at the moment, and therefore it makes sense to present Nokia service model. Other vendors might have different model or different naming convention for the same components. You will notice here also that this service model is very similar to our SPB service model. There is SAP, service, SDP. Main difference here is that network part of SPB, including transport and service tunnels, are created automatically, while in Nokia service model you have to administrate those, as we saw it before in this session. Some of them are dynamically created based on IGP, but you still have to enable LDP protocol on interfaces and targeted LDP within services for service labels. Going through this service model, we can start with customer entity, which we can also call a subscriber. This entity is needed for further creation of services as they are associated together. When you create a service, you have to specify customer. Service access point is a local entity on a router and it identifies customer interface point for a service. SDP is also a locally unique entity, and it represents a way to forward traffic from one router to another through service tunnel, which is unidirectional as it is transport tunnel it is using. One SDP has to be configured for each far-end router to which service has to be provided. SDP also required return path SDP to be created. Multiple services can be associated with a single SDP. When bounding SDP to a service, it can be done either as a mesh or spoke SDP. Mesh SDP is a concept used with SPB, while you can see spoke SDP as a traditional bridge port, and the main difference between spoke and mesh SDP is how they handle received flooded traffic. In short, flooded traffic received through mesh SDP on a node is replicated to all spoke SDPs and subs within the service, while flooded traffic received through spoke SDP is replicated to all other spoke SDPs, all mesh SDPs, and subs, of course, within the service. IP MPLS services are divided into two groups: Layer 2 services, either point-to-point or point-to-multipoint, and Layer 3 services. Basic principle of point-to-point service that is called ePipe Ethernet pipe or VLL, virtual leased line service, is that there is no need for MAC learning. Whatever traffic ingress one end of E-pipe will be encapsulated and will egress on the other end of E-pipe, and vice versa, of course. So this service is fully transparent for customer data. There could be a local E-pipe which consists of two subs on the same node, or there could be a distributed E-pipe that has two subs on different nodes and associated SDP. Then there is also point-to-multipoint layer 2 service, what is also called MPLS. So multiple sites are connected in a single bridge domain over IP-MPLS network, and all customer nodes are part of the same subnet. It is also fully transparent for customer data, but there is MAC learning involved, and there is a lot of features related to management of MAC addresses and their flashing for faster convergence. MPLS can also participate in customers' layer 2 loop prevention protocols, or could be completely transparent to it. We have already mentioned differences between mesh and spoke SDP, the way SDP is associated to this service. Then there is also eVPN or Ethernet VPN. It is one of the latest developed technologies that allows layer 2 VPLS service to operate as IPVPN. MAC learning is, in contrast to regular VPLS, now part of a control plane based on MPBGP. There are several other benefits of eVPN service, and one of the most important is also supported multi-homing for increased redundancy. There is a dedicated session for eVPN prepared by Patricio Martello, so please watch this session to find out all other interesting details about this service. So let's take a look at Layer 3 service or IPVPN. In general, VPRN service consists of multiple sites connected to one or more PEs. And while in VPLS all the sites of a single customer will be connected to a single bridge domain, in VPRN all the sites of one customer would have different local IP subnets. If you take a look at the top right corner, you could see green customer and blue customer connected to multiple PEs, but each site will have different subnets. In this example, blue VPRN will be configured on 3 PEs, and green VPRN service will be configured on 2 PEs. In addition to exchanging routes with local customer edge nodes, PE routers will exchange routing information learned from CEs on all sites via MP-BGP peering. This way, they will provide end-to-end connectivity for all the sites. Let's take a look at one site. There are 3 different customers on this site connected to PE. So 3 VPRNs will be configured, one for each customer. Blue customer has 2 customer edge devices on this side. Therefore, within Blue VPRN, we will configure 2 interfaces, while other VPRNs will have only single interface created. Each CE is peering with VPRN interface using one of the dynamic protocols such as ISIS or OSPF, or using static routing. Notice here that blue customer and green customer are using identical subnet for a local area network. Using different policies, you have to know that with VPRN and BGP there will be a lot of policies. So using different policies, local customer subnets will be learned in each VRF. As a result, you can see that routing table of Blue VPRN will have information about local network behind CE1 and CE2. We are now moving to PE to PE routing, which is done via multi-protocol BGP. Initially, BGP was created for IPv4 routing, so in order to route between VPNs, multi-protocol extensions were needed. Therefore, this version of BGP is called Multiprotocol BGP. As you remember, both green customer and blue customer use the same subnet on local networks. While those networks were still learned within different VPRNs or VRFs on a single PE, network overlapping was still supported. But in order to distinguish the same network owned by different customers as a VPN route, a route distinguisher field, 8-byte value, was added to IPv4 address, creating unique VPN IPv4 address. Of course, unique route distinguisher will be used for each VPN. This way, we can make a difference between network 192.168.11.0 for blue and for green customer. VPN IPv4 will be advertised like this to all other PEs in the network that have the same VPRNs configured. In this way, all other VPRNs will receive information about local networks behind PE from which network update was just sent through MPBGP. It might not be the wanted functionality in all cases. Therefore, to each VPN IPv4 network, a route target field will be added as well. Every VPN network could have one or more route targets added, as this is one of BGP supported extended communities. Based on policies and rules related to route target received with VPN IPv4 network, each PE in the network can decide whether to import under condition, or not import received VPNs through MPBGP updates. So route target, among other BGP communities, is a very powerful tool used by network administrators to fulfill different design requirements. Another field that will be added to VPN routes is service label. We have already mentioned that besides transport labels, labels could also be used for service differentiation. Due to service label tables, Blue VPRN at HPE know exactly what egress label will be received from Blue VPRN on each PE in the network. So to summarize, based on service label 123.123, Blue VPRN will receive network 192.168.11.0, and further on, based on a policy rule, to import networks with route target 64444-4, network 192.168.11.0 will be learned into route information base with next hop of P. As such, it will be redistributed to local C of Blue customer behind PE1 using the same routing principles between PE and CE as it was on PE2. So what about data plane? Let's say Blue customer from CE connected to PE1 wants to send data to their side behind PE2. At ingress LER, data packets will be added with service label for Blue VPRN and transport label for PE2, as it is egress LER for CE2. This info is enough to bring data towards Blue VPRN on PE2 and further on to CE of Blue customer. Let's see now about how to position IP MPLS technology. I'm sure this is not your first time hearing about IP MPLS technology. Everyone who was involved in any way with mission-critical networks faced IP MPLS already. Now, after we went through some basics of this technology, I hope it will be easier to understand their main characteristics, and I hope this loud thinking on both technologies will help you position the right one based on the network requirements of a particular project. So let's start. Scalability. Needless to say, all service providers are using IP MPLS technology. What about SPB? We have networks that are running SPB on more than 1,000 nodes, and we are confident control plane can sustain even 2,000 or more nodes, but has never been tested. Network with 1,000 plus nodes could be easily called large networks, but compared to networks running IP MPLS, so light green for SPB. Service-oriented, of course, both technologies are service-oriented and deploy virtual private networks. Overlay-underlay architecture, of course, big yes for both. Upon a single physical network, there are many virtual networks running. Secure, again, yes for both, as a VPN is considered as a secure container and cybersecurity threats could not be shared among services. Multi-tenancy, of course, both technologies support multi-tenancy and multiple customers could be managed over a single infrastructure without risk of overlapping IP space, for instance. Dynamic, I would say yes for both, as they react positively with moves, adds, and changes in the network. Adding a service requires work only on a PE or BEB of interest. Convergence. Fast reroute and 50 milliseconds convergence is a standard of IP/MPLS. Keep in mind this is LSP convergence, not end-to-end convergence. SPB convergence depends on some factors, and we are moving towards 100 milliseconds, which is also very fast and sufficient for most, but some signaling protocols. So, light green for SPB. Standard, of course, both technologies are standard-based. MPLS with Internet Engineering Task Force and IEEE 802.1aq for SPB. By the way, Nokia MPLS service routers do support SPB. While both technologies share some very strong technical characteristics, there are some other factors coming from your customers that would favor one technology over the other. You will have to go for IP/MPLS in case there is a strict requirement for 50 milliseconds convergence, or there is a strict requirement for IP/MPLS protocol. Also, IP/MPLS would be your choice in case you have to support some legacy protocols in the network, SDH, ATM, TDM, and so on. There will also be some customers that want to extend existing IP/MPLS network or to, let's say, renew part of the existing network. So again, you will have to go with IP/MPLS technology. On the other side, SPB has also some very strong points. First one is automation. As you could see before, and from your experience, the network portion of shortest path bridging is all done automatically. So you don't have to configure transport tunnel, you don't have to configure service tunnels. It's all done completely automatically. And this automation can go as far as to have complete end-to-end solution over SPB without a single user touch. So fully automation possible. Saying this, it is also clear that SPB technology is much more simpler to deploy, maintain, and troubleshoot. And of course, SPB is supported on nodes running virtual chassis, which is additional step in terms of redundancy and resiliency. And of course, it doesn't have to be one or the other. In addition to IP/MPLS core, SPB can run on Ethernet access layer, extending VPN capabilities all the way to the users, devices, or IoTs. This way, VPN capabilities could be extended also to harsh environment conditions, as SPB is running on our hardened switches built for industrial and mission-critical applications. Additional MAC security could be extended as well between core and access layer. As IP/MPLS technology is meant to run in the core of networks, it lacks strong user, device, and IoT-related features that are mandatory today at the access layer and which is one of the ALE's strong side. It is also important to mention the whole network, core to access, could be managed with a single NMS, NFMP from Nokia, and at last but not least, with other benefits Ale brings to the combined solution, there is also an advanced Wi-Fi portfolio. First of all, I would like to thank all of you who are still with me at the end of this session. Secondly, let's close with some key takeaways. The IP/MPLS technology has been used for many years now and is here to stay, as it has some unmatched capabilities in terms of fast convergence, traffic engineering, and continued support for new services such as Ethernet VPN. Some people would say that IP/MPLS is a very complex technology, and I would conditionally agree with it. It all depends on what your goal is and how do you want to achieve it. But the results of this complexity could be amazing. On the other hand, it could also be simple and automatic. The addition of IP/MPLS technology in our portfolio opens some new opportunities, as it complements other technologies that we are very strong in. If you need any assistance with IP/MPLS, please get in touch with our team and we will help you out as we are in this together. Thank you and enjoy your Spacewalkers live event.